Sean Solomon and Derek Hari of Carnegie's Department of Terrestrial Magnetism are co-authors of a paper that helps explain the origins of the Hawaiian Islands. The leading hypothesis has been that they are the result of a plume of hot material deep within the Earth's mantle.
This has been known for quite some time that you have these chains of volcanoes that form on the tectonic plates, especially the oceanic plates, because they're thinner than continental plates. And these volcanoes form chains that are age progressive, meaning that volcano ages get younger in one direction. The Hawaiian Island chain extends all the way to the Aleutian subduction zone, and the youngest volcanoes are active today, and the oldest volcanoes were erupted something like 80 million years ago. And there's a very clear chain of volcanoes that formed as a result of the Pacific plate drifting over this kind of stationary hotspot, the Hawaiian hotspot. Once the theory of plate tectonics was developed, it became pretty clear that a very easy way to do this in a physical sense is if you have the plate drifting over a stationary plume of material that's coming up from the deep mantle.
However, evidence for the theory has been sketchy.
That has been a debate because it's been so hard to get high-resolution images using seismology of the structure underneath these great hotspots, particularly at the depths of many hundreds of kilometers, where the distinctions between the classical plume model and other explanations for persistent volcanism can be sorted out.
An ambitious project known as PLUME, for Plume Lithosphere Undersea Melt Experiment, deployed a sophisticated array of seismometers on the seafloor around Hawaii. They provided the first high-resolution seismic images of a mantle plume.
So this is an outcome of an experiment that was designed some years ago to address this very question by taking advantage of a new generation of long-lived, broadband seismic instruments that could be set out on the seafloor for periods of a year at a time.
The results provided an unprecedented glimpse of the roots of the Hawaiian hotspot.
So we had suspected from geochemistry that the center of the plume would be kind of on the southeastern edge of the main island, the big island of Hawaii, and that turns out to be about where the hotspot is centered. We had also predicted that its width would be comparable in size to the size of the Hawaiian island, and that also turns out to be true. One thing that really sets this study apart from all the other studies of its type that have been done is that we can actually get very solid information and actually see this mantle plume extending into the mantle below 660 kilometers depth. And that was something we'd all hoped for, but to actually be able to obtain an image like that, it worked out exactly as we would hoped.
Critics of the plume model have argued that the magma in hotspot volcanoes comes from less than 660 kilometers in the upper mantle, not deep plumes.
Most of the competing ideas have shallow sources for the heat and upwelling that leads to melting and generation of magmas that erupt at places like Hawaii. What distinguishes the classical plume model from all of those models of shallow generation is the great vertical extent of upwelling. Implicit in that model is that the sources for the material and for the upwelling reside deep in the lower mantle of the Earth.
So, has the question of hot spots and mantle plumes been settled at last?
We believe that we have very strong evidence that Hawaii is underlain by a plume that extends down at least to 1,500 kilometers depth. It may well extend deeper, we can't say on the basis of our data, but that is addressable with global data sets now that our data have been analyzed. So it's a very strong vote in favor of the plume model. I expect a spirited debate to continue, but now it is guided by a very high-quality data set.
The research appears in the December 4th, 2009 issue of Science. This is John Strom for the Carnegie Institution.